So today I want to talk to you about contact angles and a little bit of surface physics. So first I want to remind you of the idea of a surface energy or a surface tension. In a fluid, surface energy and surface tension are the same thing. So a surface energy, remember, is the energy required to form a surface in a liquid, like pulling a drop out of the bulk fluid. And a surface tension is an energy required to deform the surface of a liquid. Now the symbol that we usually use for a surface energy or a surface tension is a gamma, and some values for gamma are shown here in this table at various temperatures. So you can see the surface tension of water is pretty large. It's about 72 millinewtons per meter, all right? Whereas something like, I don't know, ethanol, alcohol is 22. So, smaller. And then silver or liquid metal, like mercury liquid metal, is much larger, like 485, okay? So those are some typical values. Now, if you look at the equations for work, then you can see that surface tension is the surface analog of pressure. So the amount of work that it takes to change the volume of a gas is equal to PdV, the pressure times the differential change in volume. And the work that it requires to change the area of a surface is gamma dA, where gamma is your surface tension and dA is the change in area. Now, unlike an ideal gas pressure, surface tension has a force parallel to the surface. So you can see here, if you're trying to take a needle head and push it down into the surface of something like water, then the surface tension forces kind of pull up along the surface of the water as it gets deformed. Now remember, this is related to the Gibbs free energy. We've said that the surface tension is related to the energy to form or create a droplet from the bulk liquid. And form or create, you should always think of a Gibbs free energy. Now, if you hold the temperature and the pressure constant, then you can sum over gamma dA. For each interface, you'll have a different value of gamma and A, of course. And then plus mu dN, where mu is the chemical potential and dN is the number of moles or molecules of a substance. So, for example, if you have a water droplet sitting on a surface of something like glass in the presence of air, then you would have the interface between the water and the glass, you'd have the interface between the water and the air, and you'd have the interface between the glass and the air, and you'd have to sum over all of those for both the chemical potentials and the surface tensions in order to figure out what's going on. Now, if you look at the force diagram for this, for say a droplet on a glass surface, something like that, okay, then you can see that a drop would form on top of the surface. Now, you probably know from looking at tons of droplets on surfaces that it doesn't always flatten totally out, that you've got kind of a bubble-looking thing, or at least half a hemisphere or something, sitting on top of your surface, okay? So let's discuss this in terms of the physics of it. To get started, we're going to assume that we have a pure liquid on a pure solid in the presence of vacuum or a pure gas. We're not going to assume any mixing or diffusion. We're going to assume that this liquid is not reacting chemically with the surface, that it's a fizzy-sorbed surface, okay? And we're also going to assume that, the solid isn't soluble in the liquid or anything like that. We're going to assume it's in equilibrium so that all the forces balance. Now, this isn't always the case. For example, if my surface is tilted a little bit, my water drop could be sliding down. Okay, so that's definitely not what's happening here. Or if you've just placed the droplet on the surface, it might be spreading out a little bit. So that would differ from the equilibrium condition as well. So we're just going to discuss equilibrium conditions. Okay? Now, if you were to look at the forces, I'm going to leave them as gamma. Of course, gamma is not a force. It's a force per unit length. But I'm going to leave the notation as gamma so that we're not too terribly confused about our notation here. You can see that the surface tension is going to pull on the various surfaces in this direction. So the surface tension in between the liquid and the gas is going to pull in a direction that's parallel to the interface between the liquid and the gas. So that is going to be tangent to this little hemisphere right here. If you look at what's going on right at the edge of that droplet, then it would stick up and the angle would be in between the surface and that vector that we've just drawn is defined as what's called the contact angle. Okay, so that's our contact angle. Now, you've also got a surface tension between the solid and the liquid. And like I said, the surface tension pulls parallel to the interface between the two things. So if we have a flat surface, then that surface tension is going to pull in a straight line here that points along the surface. We also have a surface tension between the solid and the gas, okay? And that pulls in the opposite direction, but also parallel to the surface. Now, if we assume that this system is in equilibrium, that means nothing's moving or accelerating. So that means that all the forces are going to balance. So we could do our free body diagram and set the sum of all forces in all directions equal to 0. If we look at the equation that we get out in the x direction, the sum of the forces in x is equal to 0, then we end up with this little guy right here. The surface tension, liquid gas, right? So that's this vector that points up the angle here, times the cosine of that contact angle, that's the x component of that vector. And then pointing in that same direction is the surface tension of the solid and the liquid, okay? Now, that has to balance with the vector that points in the opposite direction to the right over here, and that's the surface tension between the solid and the gas. So if we're at equilibrium, then these two sides, the forces that point left versus the forces that point right, must balance. This equation is known as Young's equation for the contact angle. And it's a pretty well-known equation in surface physics circles. Now, what does this mean? Well, if the contact angle were to go to 0, boom, then you would have what's called wetting of the surface. The liquid would spread in a film all across the surface, okay? In that case, you have complete and total wetting. This is relatively rare, but usually what happens is you get a little drop, and the contact angle might not be very large, but it's still there, okay? So if a droplet forms, we're going to have a contact angle that's greater than 0, okay? And this is a non-wetting situation when the liquid doesn't wet the surface. If that's the case, then the cosine of that angle is something other than 1. And so you get the equation that the surface tension of the liquid gas plus the surface tension between the solid and the liquid is greater than the surface tension of the solid and the gas. Otherwise, it's going to wet. If it wets the surface tension liquid gas plus surface tension solid liquid is less than or equal to the surface tension of the solid and the gas. All right, so what does that mean? Well, another way to approach it or think of it is that if the interaction of the liquid with the solid is stronger than the interaction of the liquid with itself, then it's going to wet that surface, okay? So if we assume that the energy of that interaction, we'll call it phi LL, and that would be the energy of the interaction between one liquid molecule and another liquid molecule. And then we'll call the chemical potential or interaction of the liquid molecule with the solid surface phi LS, okay? And those are sort of the depth of our potential wells that they experience, okay, that sort of holds and binds them. So if you define the energy difference between those two things as delta, delta is equal to phi LL minus phi LS, then what that says is if your delta is less than 0, okay, then that means phi LL is less than phi LS, and the liquid wets the surface, okay? The liquid likes the surface better than it likes itself, okay? The potential well for the liquid surface is not as deep, or is deeper than the potential well for a liquid with another liquid. Now, if delta is greater than 0, then the liquid doesn't wet the surface. In other words, the liquid likes itself better than it likes the surface because the potential well for the liquid is deeper than the potential well interaction between the liquid and the surface. Hopefully that makes sense. Now, we're not discussing chemisorption here. We're not having the reaction, a chemical reaction between the liquid and the surface. It's not forming a new compound, in other words, okay? So much of the wetting properties of the system are just due to electrical interactions of the liquid molecules with the molecules in the solid. So that really brings to mind or begs the question of polarity, okay? So polar molecules are attracted to other polar molecules, for example. Now, let's use the dipole moment from physics, which I'll call here P. Some textbooks call it mu. I'm going to call it P. It agrees with introductory physics text. But anyway, it's a vector quantity, and it's the polarity to first order. So you set P equal to the sum of the vectors that point between the charges, the separation of charges, times the distance of the separation of charges. So you have your charge times the separation between those two charges, and you sum over all of that for your entire molecule. Okay? So Q is a charge and R is the separation between those charges. The little cartoon down here shows what can happen for a nonpolar molecule like carbon dioxide versus a polar molecule like water. In carbon dioxide, you have a carbon here in the middle and oxygens on opposite sides of the carbon, okay? So what that means is there's no net dipole moment because any spread in charge that goes to the right also goes to the left. It's a symmetric molecule. And so the sum is 0, right? Whereas in water here, there's an angle. So you have a hydrogen here, an oxygen here, and a hydrogen here. So that means that you have a separation, a net separation of charge. What happens is those hydrogens give up their electrons, their one electron, they give it up to the oxygen so that oxygen can have a full valence, a full outer orbital, okay? And that means that there's a net positive charge on the side of the hydrogens and a net negative charge on the side of the oxygens, and that creates a dipole moment. Actually, a pretty big dipole moment in the case of water. Now, dipoles are one thing. There's lots of different ways, lots of different types of electrical forces that a liquid on a solid or, basically any two molecules could experience here. You can have two ions, for example. If you have two ions, you're going to have a really strong force between those, and it's going to obey Coulomb's law, as you might remember from introductory physics classes. So the positive and the negative ions would be attracted to one another, whereas like charges would repel one another. Another thing that can happen is you can have a polar molecule interacting with an ion, and that also has a pretty strong force of interaction. You could also have two dipoles interacting with one another, okay? And then what would happen there is that they might line up like this, where you have the positive side and the negative side, okay? And then you have the negative side of one molecule being attracted to the positive side of the other. So they kind of line up with their dipoles pointing in the same direction. And another thing that can happen, yet another, is that you have like a dipole, okay, like water, sort of causing a separation of charge in a molecule that wasn't originally a dipole. So let's say that you have something like an oxygen molecule here. If it were by itself, then it would be symmetric and the dipole moment would basically be 0. But then it gets near an ion or a dipole, and you could pull some of the charge to one side, and a molecule that wasn't previously a dipole kind of has an induced dipole moment, okay? And then you can get dipole-induced dipole interactions. And then there's even more. You can have induced dipole interactions, and they're even weaker than that, okay? So let's look a little bit at these forces in between molecules and talk about the force and hence the strength of those interactions. So to remind us, if you have an ion attracted to another ion, that obeys Coulomb's law, where the force is proportional to the product of the two charges divided by the distance between those charges squared, okay? Now, if instead you have an ion interacting with a dipole, your force is going to be proportional to the dipole moment of your dipole times the charge on the ion divided by the distance between the two cubed, okay? So since the distance goes as the cube here, you can see that this force would naturally be a little weaker than the ion-ion force, right? Now let's say that you have a dipole-dipole force. Well, that force is going to be proportional to the strength of the two dipoles on top. You multiply those together, and then you divide by the distance between the two dipoles to the 4th power. So dipole-dipole forces are usually weaker than ion-dipole forces, although it does depend a little bit, of course, on the distance between the two and the strength of the dipole and the strength of the ion. Okay, so there'll be some overlap. Now, these dipole-dipole forces are also called Keesom forces or hydrogen bonds if the molecules have hydrogens, like water or acids. And hydrogen bonds are stronger than regular Keesom forces because the dipole moments are so much larger for water and hydrogen containing compounds than they are for your typical dipole. All right, so here we're going strength. We're going, as I continue on, the strength gets lower and lower. Okay, more bond types. Let's say that you have an induced dipole interacting with a dipole. Well, in that case, the force is proportional to the polarizability of the nonpolar thing, alpha, times the dipole moment squared divided by r to the 7th. Okay, so now the distance, it's going even stronger as the distance, which makes that force even weaker. These are known as Debye forces. And then finally, we have induced dipole forces, and those are the weakest of all. And that's proportional to the polarizability of the two molecules. I assumed here that they were the same type of molecule, but anyway, we have the polarizability squared times the ionization energy of the molecule divided by r to the 7th. Now this is the weakest by far, and these forces are known as London dispersion forces. So all these forces that have special names were just named after the people that originally developed the theories behind them and discovered them. Okay, now remember, the whole wetting situation is controlled by the difference, the delta, between the phi LL and the phi LS, right? So if the interaction energy for the liquid with another liquid is stronger than the interaction energy of the liquid with a solid, then you get yourself a non-wetting situation. Okay, so that's when the delta is greater than 0. Whereas if the liquid likes the solid better than it likes itself, right, then you're going to have a wetting situation. Okay, now what that means is that when water beads up on a surface, it's because water likes itself so much because of that strong dipole-dipole interaction, right? And that means it likes itself better than it likes the surface that it's sitting on, all right? Now here's some dipole moments for some common materials. You can see that, where's water? Right there. It's got one of the larger dipole moments in this list, okay, of 6.17. And so you can see that the dipole moment of water is pretty large compared to that of other liquids. Of course, for helium, argon, hydrogen, nitrogen, these gases, the dipole moments are practically 0, okay? Now, a perfect example of what's going on here would be Teflon. We all know Teflon pretty well as a non-stick coating. And if you put water on top of Teflon, it's got a pretty decent contact angle. It beads up nicely, and that angle is relatively large. It also has a low friction coefficient, partly because stuff doesn't like to sit on it, right? And the friction coefficient is 0.05 to like 0.1. It's one of the lowest ones out there. Now what's happening here is that polytetrafluoroethylene, which is its chemical name as opposed to its trade name Teflon, it's a very symmetric molecule. So normally if you have a fluorine in there, it likes to grab charge and pull it to itself. It has a pretty high electronegativity. But because those fluorines are on opposite sides of the Teflon chain, right? So you've got a fluorine over here, but it's balanced by a fluorine on the opposite side of the chain. So the net dipole moment for that molecule sums to 0 if you sum over the chain, okay? So the dipole moment is very low, and that makes it hard for water to wet the surface, okay? Because water is a very polar molecule and Teflon is a non-polar molecule. So water likes to interact with itself more than it likes to interact with this non-polar surface down here, and so it beads up. Right? It would much rather be next to other water molecules than try to induce a dipole in that Teflon, okay? And that's why the water beads up on the surface. So you might be familiar with a lot of the applications for this stuff. Happy Pan, as it's shown here in an advertisement from the 1960s. This substance, Teflon, was accidentally discovered in 1938 by Roy Plunkett, who was a scientist at DuPont. He was trying to make a new chlorofluorocarbon refrigerant, and he was using tetrafluoroethylene gas to do that. But during his experiment, the Teflon gas, or the tetrafluoroethylene gas, stopped flowing, and the weight of the bottle was too high for the bottle to be empty. So he got curious, and he saw the bottle open, and he saw this waxy white substance on the inside. When he tested the substance, it proved to be really super slippery, and Teflon was born. All right. Well, I hope you enjoyed that, and we're going to continue with this topic when we talk about super hydrophobic surfaces and how this whole idea of a contact angle applies to nanostructures.